In this video, I'm going to demonstrate how to solve a projectile motion problem. I'm going to begin with one that has all of the initial velocity being in the x direction. If you've got the 7th edition of the book, this is problem number 20. And the problem reads, a ball is thrown horizontally from a roof of a building 7.5 meters tall, and it lands 9.5 meters from the base of the building. And so the question that the problem reads is, what is that initial velocity? Okay, as you read through these problems, it's not going to say, oh, by the way, folks, all of the initial velocity is in the x direction. You get the hint that it's all in the x because it says a ball is thrown horizontally from the roof of the building. So that's one of those examples of information that is given to you that is not exactly clear. So the initial velocity is entirely in the x. That means the initial velocity in the y is going to be 0. And we're asking for x information. It may not appear that the information in the y is terribly important, but it is. It turns out that as we go through projectile motion problems, we're given some information in the y, and we can divide up the x information and the y information. The only thing that the two components have in common is the time. Obviously, it's one object. The amount of time that it takes to fall this length is going to be exactly the amount of time that it's going to take it to move horizontally 9.5 meters. And so what we're going to want to do, if we're going to find velocity in the x equals question mark, that's going to equal the change in position in the x over the elapsed time. You can look at that equation and say we know the change in position, but we do not know the elapsed time. Therefore, we cannot solve for information in the x. So now we go to the y information. Do we have enough information to find out what that change of time is using the y information? We know the height that this thing falls. We can choose an initial position and a final position. I like to choose the final position to be at the lowest point of the motion because then I end up with more positive numbers. So my initial position is going to be 7.5 meters above the ground. My final position is going to be 0. We know the acceleration in the y because this is a projectile motion problem. The acceleration in the y is gravity. And we know the initial velocity in the y. Because this is launched horizontally, all of the initial velocity is in the x direction. The initial velocity in the y is 0. So now we can look at those kinematics equations, and unlike in class when I have all the kinematics equations written on the board, I'm going to have you look at the list on your book because I don't have enough room to be able to show all those and still be able to put this video together. So you should look through your kinematics equations and say, what formula can I use to solve for the time that it takes for this thing to fall? One formula that works really great is going to be that y equals y initial plus initial velocity in the y times time minus 1/2 times gravity times time squared. And so if you look through here, our final position is 0, our initial velocity in the y is 0, so this formula becomes very, very friendly. Our initial position is going to be 7.5 meters. I'm going to move that to the other side. Negative 7.5 equals 1/2 of gravity is negative 4.9 t squared, because this is 0 and this is 0. So t is going to be the square root of 7.5 over 4.9. And when I solved that equation, I got 1.237 seconds, which rounds to 1.2 seconds. Okay. We found the time that it takes the motion to take place. We can now solve for that initial velocity, which is the velocity in the x. Initial velocity equals velocity in the x equals the distance that is covered, 9.5 meters, divided by the time that it takes. I'm going to hang on to a few of the sig figs on here before I round to my final answer. And when I did that, I got 7.678 meters per second, which I'm going to round to 7.7 meters per second. So that is how fast this thing launches horizontally, and that's all that that particular problem asks for. But I want to go ahead and solve for the final velocity. How fast is this thing going when it goes through its motion and hits the ground? So if we're going to solve for the final velocity, the first step would be to find what the final velocity in the x is. And to do that, we can use the equation final velocity in the y. We can solve for the final velocity in the y equals initial velocity in the y minus gravity times time. Our initial velocity in the y, as you recall, is 0 because all of our initial velocity is in the horizontal direction. So the final velocity in the y is just going to equal minus 9.8 times time, that 1.237 seconds, and that turns out to be 12.12 meters per second. And we're going to assign a negative value to it because it's in the downward direction. Also, gravity is negative. That's the way our math works out. So we have the final velocity in the y. We know that the final velocity in the x is exactly the same as the initial velocity in the x because we do not have any acceleration taking place in the x. So now we can calculate what the final velocity is as this thing hits the ground. So it's going to hit pretty much kind of like that at an angle. So we can do the vector math on it exactly like I showed you guys before. Our velocity is going to be, our final velocity, square root of the velocity in the x squared plus that final velocity in the y squared. We'll take square root of that whole thing. 12.12 squared plus 7.678 squared. And the final velocity as that thing hits the ground is 14.34 meters per second. This is the size of the velocity. When we're talking about a velocity vector that is aiming a certain direction, this is the size of it. This is what we say. We don't say a positive or negative unless it happens to be all in the positive x direction or all in the negative x direction or negative y or something like that. Because this is at an angle, we're going to need to do that next step that I talked about when we did the projectile motion and calculate the angle at which this hits. So if I superimpose this final velocity onto an xy coordinate plane, we have our positive x velocity just like this, and we have our negative y velocity just like this. The size of this is 14.34 meters per second. The angle that it hits at is the inverse tangent of the opposite side, the velocity in the y, 12.12 negative, over 7.678. And we end up getting negative 57.6 degrees, which tells us that this thing would be below the axis just like that. And so in the book sometimes it'll say 57.6 degrees to the horizontal, and you imagine if this is the ground that it lands on, this angle here, by the law of the angles that you should have learned about in geometry, would also be 57.6 degrees to the horizon. And so that is how you solve projectile motion problems. This particular projectile motion problem was a simple version in that all of the initial velocity was in the horizontal direction. So as you go through, the first step always is to see what components are your x components and your y components. We don't need to take our initial velocity and figure out what the x and y components are right now because we are told that it's in the horizontal direction. All the initial velocity is in the x. And so we can you lay out the information that we have. We find out we don't have enough information to solve our problem completely using x data. And so then we look for what we know in the y direction, and it turned out we were able to solve for time using the information that was given for the y direction. The time that it takes this thing to fall is going to be exactly the same amount of time that it takes this to move in the x direction. So we take the time that we got and we can put it into our x equation to solve for our x information. Anyway, we keep our x and our y information separate, and then we add them together at the end using vector addition.